So we have been talking about work in the last lecture. Now let's talk something about energy. Okay. Again, I would introduce you guys with few terminologies, and then we would look at something related to heat transfer. Okay. You have a question? Okay. So let's talk about energy. Okay. So generally in thermodynamics what we do is we talk about some other types of energies. Most of the time those energies are related to so for energy, what we can say is, till this time we have been talking about potential energy, we have been talking about kinetic energy. Generally those kind of energies are considered in mechanical systems. Mechanical system means if you talk about, let's say, any spring, you are trying to compress it or you are trying to stretch it. What you have been doing is you are trying to change the body shape of that spring. Right, you are trying to stretch it, you are trying to compress it, and by that body change some kind of energy is stored into it. Okay, and once you release it from that compressed position or stretched position, that spring tries to come to its original position. Okay, it tries to retain its original shape. So you can say that through this potential energy changes into kinetic energy, and kinetic energy keeps changing into potential energy. So this goes on till the time it again achieves equilibrium and everything becomes like at a steady state. Now the point is, in thermodynamic systems we have few other types of energies as well, because we need to deal with temperature. Now that temperature is also taken as a measure of, you can say, the kinetic energy of molecules, and you can say the potential energy of molecules. I mean, the kinetic energy of molecules is of different, again it has different types. For example, those molecules oscillate. Similarly, you can say oscillate or vibrate, these are two synonyms. Similarly, they also try to rotate. Okay, so it's a rotational kinetic energy, then they have translational kinetic energy. At the same time they collide with each other. That's how they transfer their energy to the next molecule. Now this is something which is a microscopic approach. Once you talk at the level of molecular scales, it means you are talking from the perspective of microscopic things. Now in thermodynamics at this stage, obviously we need to talk about macroscopic things. We would be talking about the overall behavior of the system. Now to look at that overall behavior, what we do in thermodynamics, we try to introduce another term which is known as internal energy. Okay, so you can say in thermodynamic systems we have following types of energies, you can say, or following forms of energy, whatever you call. So this is something which is kinetic energy, that is associated with the motion of the system as a whole. Now why do I need to write this phrase as a whole? Because we are talking about macroscopic things. Okay, so as a whole, and obviously we would try to quantify that kinetic energy, or let's say velocity or displacement, whatever that is, we would try to quantify it with respect to an external coordinate reference frame. Okay, the second form of energy would be gravitational potential energy. Yeah, for example, if this is a system, let's say this is a system which you are talking about. It can be any arrangement. Now if it is moving, obviously to measure its velocity, you need to have some origin first. You need to set some reference axis first. For example, you would say that this direction is horizontal x-axis, this is y-axis, this is z-axis, and then you, let's say, take that point as origin. So then you would be able to measure its displacement, right? So for example, if I take origin at the other corner of this room, obviously everything would be computed relative to the other point. Okay, so then obviously the magnitudes would be different than the first case. So gravitational potential energy, again, that is associated with the system, associated with the position of the system. Again, as a whole, we won't be talking about the position of a molecule in a gravitational field. We would be talking about the whole system in Earth's gravitational field. And finally, there is a third form of energy which takes everything into consideration, all other forms of energy, are lumped together in the internal energy of the system. Now, there is one very important point to understand, that once I talk about the kinetic energy of this system, let's say this board marker is a system. Now, for example, it is moving. Obviously, it has its kinetic energy as a whole, as a system. But if you talk about the kinetic energy of the molecules of this system, or the atoms of this system, they are different from this thing. Okay, so please try to understand that first form of energy was related to the system as a whole. The second form of energy was related to the gravitational potential energy of this system as a whole. I am not talking about the molecular scale. So whatever comes next, that is the internal energy, that takes into account the kinetic energy of the molecules, which includes the rotation, vibration, oscillation, collision, everything. And the second thing is, obviously, that internal energy takes into account which is known as the bonding between the atoms or molecules. Okay, I am talking about the bonds. So you can say every other thing would be taken into consideration in this definition, internal energy. Not the total energy. Not the, just try to understand these three things. There is first form, which is the kinetic energy. There is the other form, which is the gravitational potential energy. And then there is something which is known as internal energy. For example, if I ask you that there is a gas contained in a cylinder and you try to stir it with a fan. For example, you try to stir it with a fan. Now what happens is, are you trying to change the kinetic energy of the system as a whole? whatever the gas is there inside the container. You are talking about the container itself, right? So for example, are you talking about the gravitational potential energy of that system? Or are you trying to change the kinetic energy of the molecules, or let's say all the gas particles? Obviously that would change. So you would say that something has happened, some change has happened to what form of energy? Internal energy. Okay. So just like any other energy form or work, obviously work is not a property. So energy is an extensive property. We have already talked about it. Internal energy is also an extensive property. You need to add them up at different points, and then you can say that overall energy is addition of all the points. Generally it is described as capital U. We use this word in denotation. Internal energy is represented by U, and if you use smaller u, what does that mean? Come on. Yes, this is internal energy per unit. Yes, this is specific internal energy. I hope you understand what was specific volume. So it is something similar. On the similar grounds, you can say that it is specific internal energy. Okay. Now all the energy types are extensive property. Energy itself is an extensive property, right? We have talked about it. Just like volume, energy is an extensive property, and so is internal energy. It's a form of energy. Okay. So what we can see is, if I describe in any thermodynamic process, if I describe change in energy for any system, E2 minus E1, change in energy in any system, so you can say that it would be a combination of three things. Change in kinetic energy, change in gravitational potential energy, plus change in internal energy. Okay, so you can say that mathematically E2 minus E1 would be what? I hope you understand the notations which I am using. And by the way, this internal energy is being represented by U, so I would use this thing. Sorry? No, I think I should repeat. My point is that there is something which is this kinetic energy of this system as a whole. Now, once you look at this motion, once you look at the velocity of this motion, do you consider anything about the kinetic energy of the system as a whole or kinetic energy of the molecules in this? You talk about the system as a whole. But there is something going on at the molecular scale as well. So that something is taken into consideration as the internal energy. This kinetic energy is something different than that. This potential energy is something different than that. Okay, so those energies which are there at the molecular scale or at the atomic level, that is being considered under what? Internal energy, right? And remember one thing, there is a very important concept. By looking at the definition, you should not be, you can say, misguided that this internal energy is kind of a microscopic property. Not at all, right? We would see, as we progress in this course, we would see that internal energy is taken as macroscopic property. This is very interesting. I mean, if you look at the definition, if you look at the philosophy, it looks like as if it is a microscopic property. But once we progress in this course, you would see that internal energy is taken as macroscopic property, and generally we take help from the empirical data to prove this thing. Right? Now, what kind of empirical data? I hope you understand when I use the word empirical data. Do you understand that? I mean the data which is gathered from the experiments. Right? So, what that microscopic property is, basically it's on the molecular scale, and we were talking about the empirical data, the data which is gathered from the experiments. Now, for example, if I ask you that in engineering, whenever you try to analyze any system, there are few approaches. One approach is you always go by the fundamental principles. Now, what are those fundamental principles? Law of conservation of energy, law of conservation of mass, or let's say Newton's law of motion, second law, right? These are something which are known as fundamental laws in science, because nature generally behaves following those laws, right? So my point is, if there is some situation where you are not in a position to apply those fundamental laws onto some system, the system becomes very complex. Now, for example, I can just give you an example for it. Let's say you talk about motion of a molecule. Can you apply Newton's second law on that molecule? Not at all. Now, what you would be doing is, you would be trying to perform some experiments and try to gather some information out of it. Okay, so if you do your analysis based upon this thing, you would say that you are doing it by what? Empirical data. And if you deduce some kind of relationship, I hope you remember that curve fitting which we talked about in the last lecture. So that curve fitting is what? That is something which is empirical curve, empirical relationship. Okay, so, and I hope you understand what that polytropic process is. I used that term in the last lecture. So what that polytropic process is, if you write it as PV raised to power n equals constant, obviously the constant term, it is 1, 2 or whatever the magnitude is, or let's say the exponent n. This is something which is coming from that curve fitting, right? So for some processes you may have PV square equals 1. For some processes you may have PV cube equals 3, right? So these are some things which are coming from the empirical data. So you can say that this property is taken as please. I think I need to consider few things first. I need to check few things first, and then I would be able to comment on it. Okay, because I do not remember the basics of that law. So please let me check that, and then I would come up with my opinion. So please remember that question. I would try to answer it. So U2 minus U1, it is taken as a macroscopic property as far as the scope of this course is concerned. Okay, so now I hope you already know the difference between microscopic and macroscopic, right? So these are few things which would you can say generally students are confused about it, when to take that property as a macroscopic, when to take it as a microscopic, because we are talking about of the subject at a macroscopic level. So we should be looking at the macroscopic properties only. Where does that internal energy come from, right? So these are just confusion, so that is why I am spending much time on it. The second thing is, let's talk about heat. Now, heat is something which flows once you establish some kind of contact between two objects with different temperatures, right? So you can say it's a form of energy. It's a form of energy. That is something which flows when you establish I should not say the physical contact, I should say contact only, when you establish some kind of contact between. Now why I did not use that physical word, I would also tell you. Once I would talk about different modes of heat transfer, I would say that. Just give me a minute. You establish contact between two bodies with different temperatures. Okay, so you can say it's a form of energy. Now the point is, again, can you say at some point, let's say at this state you have this much of heat? Can you say that? And for example, if I say that once the system has moved from point 1 to point 2, now at point 2 it has heat Q2, at point 1 it has heat Q1. Can we say that? No. Just like we cannot say that at point 1 W1 work is there, at point 2 W2 work is there. So heat is not a property itself, right? So just by virtue of your common understanding about these forms of these energies, so you can say that heat is not treated as a property. So for example, if I try to describe how much heat has been flowing from, let's say, from point 1 to point 2, for example, if I say that, obviously I would use this symbol Q, right? And you would take it, what kind of integral? In exact integral, and you would represent it by like this, and you would say that this is something, you represent heat like this. I hope you understand the application of that inexact integral. I talked about one case in the last class. Once I would try to find out some integration related to the polytropic processes. You understand? You remember that? Once I integrated PV raised to power n, something like that. Okay. So this is something which is inexact integral, and regarding the sign convention, this heat flow is taken as positive once heat is transferred to the system. Similarly, it would be taken as negative once heat is transferred from the system. Now, this is something which is very interesting again. No, that's why I did not use the word physical contact. I mean, that's why I just ignored that word. Okay. So now just look at this definition and tell me, there is something which is kind of contradictory from our definition for work. You remember that if you try to do some work on the system, and I gave you a reading assignment on that, if you try to do some kind of work on the system, it should be negative. And obviously if heat is transferred to the system, obviously it would be doing, finally it would be doing some kind of work on the system, isn't it? Now the point is, at the same time you are doing work on the system, but by doing what? By providing heat to the system, by providing energy to the system. So if the energy is heat is being given to the system, you are taking it as a positive thing. But at the same time, you are taking that work done on the system as a negative thing. So this is kind of, you can say, a conflict, a contradiction. Now my point is that this is something which is, those sign conventions, all of those sign conventions, they are related to the scientists and engineers who have developed this subject. Now this thermodynamics as a subject, it was developed by those who were designing some kind of heat engines, or let's say those, what should I say? Yeah, you can say the heat engines most of the time. So those conventions were used by them. Why? Because some kind of heat is being done. So just to make their equations, mathematical equations consistent, they have used this sign convention. So don't try to find any logic behind them. Okay, so you can say this is something which is traditional in the scientific literature, and it is basically it finds its root on the work which has been done by those scientists who has developed this subject. And by the way, just to make their mathematical equations consistent, they have used this kind of sign convention. So don't try to find out any logic behind it. Okay, so
in case of a gas, if we supply the heat, then at the end the gas expands and the system does work from that point. Then it makes sense the heat supplied is taken as positive and then the system does work.
Yes, exactly. Now what you are trying to do is, you are trying to make the things consistent. Do you understand that? So this is something which is known as mathematical consistency, right? So you are trying to do it for your own convenience, so that you don't find any kind of anomaly in any kind of description, right? So my point is, they have done it just for the sake of their own convenience, and you can find some kind of logic behind them as these are consistent things. Okay, so there is mathematical consistency. So that was the point which you should understand. Now I would talk about few heat transfer modes. Although this is not a topic directly related to thermodynamics, but you should understand that. So I hope from your elementary physics course, you should know what kind of heat transfer modes we have. Those are what? Conduction, then we have convection, and then we have radiation. So which of these mechanisms does not require any physical contact, physical medium? This is the radiation. That's why I just disregarded that word. So radiation is the only mechanism does not need any physical medium. So if I just look at conduction, generally conduction occurs in only one type of medium. Now for example, what I can see is, this is a block, this is a block, and these are few different molecules over there. If you put this side at temperature T1 and put this side at temperature T2, and T1 is greater than T2, obviously energy would start flowing from here to here, right? Now the point is, how would that energy be transferred from one side to the other? Obviously this temperature is greater, so the vibrational or kinetic energy of these molecules would be larger than that for these molecules. Due to that, these molecules gets excited and they try to oscillate with larger amplitude, right? And then during their oscillation they collide with the other molecules, and as a result of that collision they transfer their kinetic energy to the other molecules, and that's how heat is transferred in conduction. Okay, so you can say this is the mechanism for conduction. And how do you mathematically define it, or you can say the law to govern this conduction? Again, this is a Fourier law. This is known as Fourier law. You might have spelled it like Fourier law, I don't mind it, but generally it is Fourier law. So again, this Fourier law is kind of an empirical relationship. Now, why is it an empirical relationship? Because it has not been deduced from fundamental principles. You did not apply any kind of law of conservation of energy on a system and then you came up with this. No. What people have done is, they have seen that heat transfer rate, now I am not talking about heat transfer amount, I am talking about heat transfer rate. Heat transfer rate means amount of energy transferred per unit time. So you can say heat transfer rate is I am using this word Q dot. Generally you would see I have already described it once, that this is heat transfer rate. So you can say heat energy transferred per unit time. So Fourier determined that this Q dot is kind of proportional, or it is dependent on few things. It is dependent on temperature difference between 2 points, and it is inversely proportional to the distance between those 2 points. Okay, larger the distance, you would have smaller the heat transfer rate. So he determined that, and this is something which is experimental. So that's why I use the word empirical, although it is not that hardcore empirical which we used in the technical context, but still you can say it's kind of an experimental or empirical relationship. So once you establish some kind of equality from this proportionality, you would say that this is T2 minus T1 over delta X, or I should, and once you converted this proportionality into equality, there is a constant of proportionality which is known as thermal conductivity. Okay, so this thermal conductivity is a material property, remember that. It is a material property. It means if you choose some other material, let's say instead of a gas, if you use, let's say, some kind of solid, thermal conductivity would increase. So just by looking at this, or let's say the description which I have already given to you, how those molecules transfer their energy, what do you say? Thermal conductivity of a gas would be greater, or let's say thermal conductivity of a solid is greater? Obviously solid, right? Why? Because those molecules are densely packed and they can transfer their energies to the next molecules more easily. Okay, so that's the thing. And yeah, this is Fourier law. At this time I won't go into the details of this, because this is something, the details of all these modes, or let's say heat transfer mechanisms, this is a subject which you would deal in heat transfer code. Okay, so